Welcome everybody to this webinar on our PTP solution given by Kit, one of our support engineers. So PTP was something that we released recently with the release of the new INS, the XNAV 650. We have a number of other webinars. If you are interested, I will put a link in the chat so you can have a look at other webinars. And throughout this webinar, if you have any questions, you can ask them in the chat box on the right, and we will get back to you throughout. And then at the end, we'll have some time to go through those questions. So without further ado, over to Kit.
Cool, thank you, Jake. Yeah, so the topic of this webinar is PTP, and we'll go over what PTP is, why people use PTP, and how it works, sort of behind the scenes, and then we'll focus on how to enable it on OxTS products, how to configure it, and then sort of how to monitor it and check that it's been set up properly at the end as well. So to start off with, what is PTP? Well, PTP stands for Precision Time Protocol, and it's just used to synchronize two clocks that are connected to the same network. PTP is a standard, so it's not something that we've sort of invented. It's something that's used sort of fairly widely, and it's defined by the IEEE 1588 2008 protocol, which is known as PTP version 2. There was a sort of an earlier version, which was sort of developed in 2002, which is not backwards compatible with the second version. So OxTS were using the 2008 version. Yeah. Why would you use PTP? So as I mentioned, PTP is a method of synchronizing clocks on a network, and as the name suggests, it's very precise. So it allows synchronization of up to sort of sub-microsecond levels, which is more precise than NTP. Also, because it's achieved just by sending packets over a network, the setup only requires an Ethernet connection, so it's a lot simpler than alternative methods that customers of OxTS products would have been using up till now. So how does PTP work? We're just going to have a look at the sort of terminology which is used when talking about PTP products, and then we're going to move on to the actual synchronization mechanism. So to start off with, once you connect sort of multiple PTP capable devices to the same network, they have to establish a hierarchy. So to do this, devices send out what's known as a sync message, which contains information about how accurate the clock on their device is. And then the device with the most accurate clock becomes what's called the grandmaster, which sits at the top of the hierarchy. Then any devices connected directly to the grandmaster are slaves, and the slaves are synchronized to the grandmaster so that their time is in sync with the most accurate clock. And then once they have synchronized to the grandmaster, any devices which are connected directly to them but not directly connected to the grandmaster will also be synchronized in a sort of second step, and then sort of any devices connected to them, and so on and so forth. So to give a sort of example of how this works, if you've got a bunch of clocks connected to different switches, like shown in the picture, one of these will be the sort of most accurate clock, and that will become the grandmaster, and then all of the devices connected directly will be slaves to that and will synchronize to the grandmaster. And then the clock, which is sort of shown as a watch here, because it has devices also connected to that device but that aren't connected directly to the grandmaster, the watch also acts as a master then to these two slave devices. So these three devices will synchronize to the grandmaster, and then these two will synchronize to this master, which is also synchronized. So now we'll have a look at how the synchronization between a master-slave pair is actually achieved, and it's achieved by the exchange of time-stamped messages. So this is, we're going to just sort of work through an example. On the left, we have the main or master device, and on the right, we have the secondary or slave device. To start off with, the time on the master is 100 seconds, and the time on the slave is 80 seconds. So they're 20 seconds out of sync with each other. And the first packet, which is sent out from the master, is the sync packet. So this is sent out at a time of 101 seconds on the main clock, and the device actually saves the time at which it sends out this message. So it's saved sort of for the future, the 101 second timestamp. This sync message then arrives at the secondary device or the slave, and this arrives at a time of 83 seconds. So there's a 1 second delay before the message is sent, and then you can see, so this would be actually sent at 81 seconds. And then it takes 2 seconds for the sync message to actually arrive at the secondary, which is why the time on the secondary when the sync packet arrives is 83 seconds. And then the device saves this timestamp for the future as well. So next up is a follow-up message. So the follow-up message is also sent from the master to the slave. And this message actually contains the timestamp of when the sync message was originally sent. And the reason it's done this in two separate messages rather than just sending the timestamp in the original sync message is because that might cause extra delay to the sync message being sent out, and then the timestamp might not be completely accurate. So it's quicker to just save the timestamp and send the sync message and then send the timestamp in the follow-up message later on. So again, the follow-up message sort of arrives, takes 2 seconds to arrive at the secondary. And then when the follow-up message arrives, the slave device has 2 timestamps. It has the saved timestamp of when the sync message arrived, but it also now has the timestamp of when the sync message was sent. So it can find the difference between these two, so the difference between 101 seconds and 83 seconds, which is sort of 18 seconds, and it can apply that offset to its own time, leading to 103 seconds. So now the only difference between the secondary clock and the main clock is 2 seconds, which is the sort of transit time. So that's step 1 of the synchronization. Step 2 is to deal with the sort of offset which comes from the sort of transmit times. So the third message sent out is a delay request message, which is sent from the slave, actually sent from the slave this time to the master. The slave device saves the timestamp of when it sends this message, and again the master just saves the timestamp of when this message arrives. And then the final message is a delay response message, where the master sends the timestamp of when the delay request message arrived back to the secondary or slave device. And now the slave knows when it sent the message and when it arrived. So these two are 4 seconds apart because there are 2 transit delays. So one from the original 2 messages, and then one from the delay in the delay request message. So to work out the transit time, the slave just has to half the difference between the time when it was sent out and the time when it arrived. So half of that, the difference between these two is just 2 seconds. So that's how you can apply the two. And now both clocks show 112 seconds. So they are now in sync. So that's a sort of simplified example of exactly how the synchronization method works. There are some assumptions which are made during this. So it assumes that the transit time for a message to be sent from the secondary to the main is the same as if a message was sent from the main to the secondary. So this is a reasonable assumption, but it becomes sort of less and less true if you have more and more devices in the way between your main and your secondary clock. So for example, if you have lots of network switches, they might have a different protocol for sort of forwarding messages on, and if there's like a huge network traffic, for example, that might cause messages to sort of flow more quickly in one direction than the other. Another assumption is that the main and secondary clocks can accurately measure the time when a message is sent or received. So that's obviously vital for the timestamps being saved on each device to be correct. And that the exchange of messages occurs over a time period that is so small that the offset appears constant. It's just worth mentioning at this point that OxTS devices which are implementing PTP can only be set up as PTP masters, so they don't behave as PTP slaves, so they can't be synchronized to another device. They can only be used to synchronize other devices. So now we'll have a look at the sort of hardware setup which is required for PTP to work. Firstly, the INS needs a primary antenna to be connected, and that's because the INS gets its time solution from the GNSS satellite. So if it hasn't got an antenna connected and receiving satellite signals, then it won't have its own time solution. PTP devices also just need to be connected to the same network, so you just need an Ethernet connection between your INS and whatever device you want to be synchronized. Direct connection leads to the best performance. So if possible, directly connect the INS to your PTP slave. So when we were testing this feature, the use of network switches does reduce the performance, but you can still get the accuracy required to make an accurate point cloud with a network switch in the setup. You can buy PTP capable network switches, but they are very expensive because they require sort of hardware which is able to sort of save timestamps accurately and stuff like that. So we actually just use sort of non-PTP capable switches in our testing, and the results were perfectly acceptable. So if we compare this hardware setup to previous methods of achieving time synchronization with other products, so if we look specifically at the example of LiDAR, for example, LiDAR customers used to have to use the PPS pulse, which was output from the digital I/O port of the user cable. So this required sort of connecting the pins from the DIO port to the interface box of the LiDAR, which is a bit complicated, and you had to also enable NMEA messages to be sent either via Ethernet or sort of via the serial. So it's a bit of a long-winded method. However, with PTP, all you need to do to connect to the LiDAR via Ethernet. So it's a much sort of more straightforward hardware setup. So that was PTP sort of in general. Now we'll have a look at specifics for OxTS products, including which products support PTP. So PTP support has been added to the XDev firmware. So only products which run XDev, which will be the next generation of the large units, so RT3000 v3, Survey Plus v3, and the sort of RT500. The new sort of XNAV 650 also can run this feature, and 1003 and XNAV 550 products as well. For the XDev version, it needs to be the latest, or at least 2012-21 version to be able to run PTP, because this is the time in which we introduced the feature. So the version name is just the date in reverse. So this is 2020 December 21st, and that's when we released this feature. So now we'll have a look at how to set up and configure PTP on our products. To enable PTP, there are 4 steps. Some of these you'll only have to do once. So for example, updating the firmware. So if your firmware is not on 2012, 21 or newer, then you'll have to update it, but you'll only need to do that the first time. PTP is also feature code protected, so you will need a feature code. You'll need to buy a feature code to enable this feature if you haven't already, and then you'll need to unlock the feature in navconfig, but again, you'll only have to do that one time. And then all times that you use PTP, you'll need to make sure that the advanced command is enabled _PTP is contained in the mobile.cfg file, so in the configuration of the device. And there's also 2 additional files which need to be on the unit for PTP to work. So this is a ptpd conf file and a loopseconds.list file. And these are can be found attached to the quick start guide, which is on our support site. And I'll show you the link to that later on. If you purchase PTP, then you'll also be given a link to the quick start guide where you'll be sort of directed to download the files as well. Additional notes for configuration. So currently PTP is not compatible with Wi-Fi. So if you have an RT3000 v3 or a Survey Plus v3 and you have an internal Wi-Fi module, that will need to be disabled whilst you use PTP. Also, depending on what time format your PTP slave is expecting, you can choose different epochs. So by default, the INS will output time in GPS time, so number of seconds since the GPS epoch in 1970, but you can change that to be the sort of Unix epoch. You can also use a UTC time mode so that the leap seconds are also taken into account, and also PTP has its own epoch. So if your PTP device uses the PTP epoch, then you'll need to use that mode. So yeah, it's just important to check which epoch the PTP slave is expecting, and then to use that. All of the other configuration of PTP fields occurs in the ptpd.conf file. So you just have to open that in a text editor like Notepad++, for example, and sort of change the fields accordingly. So this is an example of one of the fields. So they'll have a couple of lines of text which are sort of preceded with a semicolon, which describes the field and gives you the configuration options. So here we're looking at the Ethernet transport, the options being IPv4 or just the standard Ethernet, which is the layer 2 option. And then the line which doesn't start with a semicolon is the configurable line. So you just choose whether you want IPv4 here or Ethernet. So all the fields are sort of laid out like this. And you're usually just given options, or they're yes or no, or it's just like a number that you need to input. So that's configuring PTP. Now we'll just have a look at how to check PTP is up and running. So firstly, there is a new status message in nav display as of nav suite 3.2. And these are the possible values that you can have for that message. And obviously the state you're looking for is 6 master. So if your PTP status is not 6, then there's possibly an issue. And the second option is to use Wireshark. So Wireshark just allows you to view the sort of network traffic on that's connected to that's coming into your PC. And if you use the following capture filter, so host 22.4.0.1.129 or host, well, I won't read it all out, but it's on the screen. This capture filter is also in the quick start guide if you need it later on as well. And this just shows you the PTP messages instead of viewing all of the like NCOM messages and LiDAR packets and stuff like that as well. And here you can see the messages that we were talking about in the synchronization mechanism earlier. So you can see the sync, the follow-up, the delay request, the delay response, etc., etc. If you are only seeing sync messages, that just means that your INS is set up correctly as a master, but there's no PTP slave on the network as well. And then if your PTP slave is sort of on the network, that's when you'll start seeing the delay request and delay response messages start to show up. So now just a couple of notes on troubleshooting. So there were a couple of sort of common issues that came up during the testing of this feature. Firstly, if you connect your PTP slave to the INS before the INS has achieved a time lock, the INS will output a timestamps of 0 seconds because it hasn't yet received the time from the satellite signals. And what happens is the PTP slaves can actually synchronize using these 0 second timestamps, and then their clock synchronizes to 0 seconds, which would be the sort of 1970 in the GPS epoch. And then when the INS does actually get a time solution, the time on the INS side will jump to 2021. But some PTP slaves ignore large time jumps, so they won't follow the PTP master into 2021, and instead it will just stay stuck in 1970. So the workaround for this issue is just to make sure that your INS is connected to the antennas and receiving signals before you actually connect your PTP slave to it. The second issue is to do with the leap seconds message. So there are lots of different implementations of PTP, and the version that we've used, which is PTPD, it actually sends the leap seconds in a sort of separate message from the timestamp signal. So you'd have leap seconds and the timestamp separately, whereas some PTP devices only look at the timestamp. They don't look for this extra leap second message. And if the PTP slave is ignoring the leap second message, then you'll have an offset of 18 seconds, because there's currently 18 leap seconds. If you're seeing this issue, then you can, for LiDAR customers, you can introduce a 18-second offset in georeferencer. For non-LiDAR customers, you can also add the 18 seconds into the actual timestamp signal using the custom offset command. And I'll link an article to that issue later on. So that's sort of covering all of the information, but now we're just going to go through a sort of step-by-step example of using PTP with a Hesai LiDAR to produce a point cloud, so that you can see all of the sort of steps in action. To start off with, we're just going to enable PTP on the device. So we're just going to check, firstly, using nav display, what OxTS version we're running. And to do this, we'll just go to widgets, digital. This will bring up the add digital measurements window, and then just search dev. And it's this second message, advanced development kit development ID. So if you just toggle that and press OK, then you get shown your OxTS version. So in this case, it's 21.04.22, which is newer than the 2012-21 version, which PTP was introduced in. So that's fine. We won't need to make any changes. If your OxTS version is lower than 2012-21, then you'll need to get an OxTS upgrade from OxTS. Step 2 is to check the feature code has been enabled. So the best way to do this is to go to nav config, click modify configuration once you're connected to your INS, and then you can click the white I button in the bottom left-hand corner, and it shows you all the feature codes. And then PTP is just on the in the top 10. And here we can see it's enabled. If it's disabled, then you'll need to request the feature from OxTS. It is a paid for add-on, so you would have to pay for this feature. Step 3 is to upload these two leap seconds and ptp.conf files onto the unit. So you can download these files from the quick start guide, and then just open a file explorer window, type ftp : / followed by the IP address of your INS. And that will show you all the files on your unit, and then you can just paste those into this window, and then they'll have been uploaded to your device. And step 4 is to add the advanced commands. So enable _PTP needs to be there. So this is in nav config, modify configuration, and then go to advanced tools section, and then the commands tab to enter these. And if you're going to change the time mode that you're using, then you need to enter a command here as well for choosing the corresponding time mode. And then you just commit the configuration, and it will all be set up. And then just open Wireshark just to make sure that you're seeing PTP packets. So again, using the capture filter that I showed you earlier, which is contained in the quick start guide, and then you're just looking for sync messages from the source of your INS. So the source here shows you the IP address of the device which is transmitting these messages. So you'd be looking for the IP address of your PTP master, and then you'll be looking for sync messages to make sure that that's set up correctly. So next, we'll just be setting up the hardware. So making sure that your GNSS antenna is connected, and then you're connected to the PC. And to start off with, I don't recommend connecting the LiDAR straight away, just to avoid that issue of the LiDAR being stuck in 1970. So I actually do the sort of initialization and warm up of the INS first, before actually connecting the LiDAR to the network switch. At this point, I'll again check Wireshark. This time I'll be looking for the delay request and delay response messages to make sure that the slave is interacting correctly with the master. There is also a web interface for the HESI, which you can use to check the PTP status. Whilst I'm on the topic of that, the PTP statuses for the HESI are either free running, which means that it's not synchronized at all. Tracking, which means it is synchronizing to a PTP master, but the time synchronization is the offset from the master is currently more than 1 microsecond. And then the final status is locked, which means that the offset from the master time is less than 1 microsecond. I would say don't worry if you're not in the locked state, because 1 microsecond is difficult to achieve with a LiDAR because of the amount of network traffic that LiDARs sort of pump out. They pump out so many packets onto the network, which affects the sort of performance of the PTP. So in my experience, the LiDAR usually stays in the tracking status, but this is perfectly fine. It's more than accurate enough to achieve a good LiDAR point cloud. So now everything's set up, you can just perform your LiDAR survey. I won't go into how you do that. Then you just need to collect your files, process the results using OxTS georeferencer. If the PTP, if the LiDAR in this case, is requiring UTC time and it hasn't used those leap seconds, then you'll just need to add a little time offset into the advanced commands section here in the processing options. And then you should be able to process a point cloud and open it up, and the results should be as shown, nice and pretty pictures, just as we were looking for. So that's all of the information I was going to cover. Here are the 2 articles which I mentioned sort of throughout: the quick start guide, which contains the PTP files that you need for configuring PTP. And there's also a guide to time modes here, which sort of discusses the sort of leap seconds issue as well. So these 2 are both on the support website, so support.oxts.com. If you just search PTP, they'd both come up. So that's how you'll find those in the future. And thanks for listening. And now we'll have a bit of time at the end to go through any questions that have been submitted throughout the webinar.
Thank you, Kit. So yeah, if you do have any questions, just put them down in the chat box. We don't have any questions yet, and that's okay. If you don't want to ask one here, but you do want to ask us a question, you can always email us, and we'll get back to you as soon as we can. And do remember that we do have a range of other webinars throughout this month and going into just this month. This month we have some more webinars, particularly support webinars. So if you're interested in any of those, you can sign up to those on the website. So we'll give it about another minute, and if there's no questions, then we'll call it there.
Yeah, just for some additional information for you, if you have, well, Jake has already covered the webinars front, but if you go to support.oxts.com, not only will you find the PTP Quick Start Guide, but there's also lots of feature guides and troubleshooting articles written by the support team at OxTS. And also, if you have any sort of feedback on our software or products, so any future features you'd like to see, then email those to ideas@oxts.com. This email address is monitored by our product management team, so they're the ones making decisions about where to take our products for the future. So that's the place where the feedback should be.
Yeah, so we don't have any questions yet, so I think we can call it there. And thank you everybody for joining us, and thank you for Kit presenting this.
Cool, thanks everyone, have a nice day.